Starting with this section, we try to address some of the issues that arise with the concept of space falling to Earth. The biggest question is, where does space go? As shown in this animation, we see that space accelerates as it falls to Earth. It moves faster as it gets closer to Earth, which is consistent with greater time dilation. Starting in the late 70s while studying the Big Bang, several scientists came to the conclusion that it was not the result of a big explosion, but rather the result of expansion of space. Space was expanding at some point, billions and billions of times faster than the speed of light. While space was expanding, it was taking matter along with it, at superluminal speeds. This was not an increase of the kinetic energy of the universe. The matter in expanding space was not moving with respect to space itself. If space is expandable, we might also presume that space is compressible. Within Earth's space bubble, new space is being sourced here at the edge of the bubble, while space is being compressed in this area here inside the bubble. Please note that there is no law for the conservation of space. Therefore, no current laws are being broken. Since space has no mass, no laws for the conservation of energy and momentum are being broken either at this point. Let's now consider a block of space as it falls to Earth. The speed at the bottom is faster than the speed at the top. The acceleration at the bottom is also faster than at the top. This would mean that space is expanding in a direction perpendicular to the Earth's surface, even as it is being compressed in a direction parallel to the surface. Here is a chart for the rate of vertical expansion of space as it falls to Earth. The compression is measured in meters per second, and the altitude is measured in kilometers. The scale is logarithmic for easier viewing. The chart plots the difference in escape velocities between 2 points 1 kilometer in altitude apart. This effect has a very important impact on free-falling objects. Looking at this chart again, we see that the first light in the universe was formed around 380,000 years after the Big Bang. This light was in the visible region. Due to the expansion of space since then, this is now in the microwave region. It is called the cosmic microwave background radiation, and it is the subject of many studies. Let us start by considering two solid objects that are allowed to free fall to Earth from a distance of the Moon's orbit. One object starts with an initial velocity of 0 meters per second relative to the ground, and the second object has a downward initial velocity of 2,880 meters per second. At that altitude, the escape velocity from Earth is 1,440 meters per second. This chart shows the difference from the escape velocity for the two objects as a function of their distance from Earth. Notice that the speed difference from the escape velocity continually decreases for both objects as they fall. Expanding space causes the objects to lose momentum as they fall, much like expanding space after the Big Bang turned visible light into microwave radiation. This is better illustrated with the following animation. In this example, we have a puck on an air hockey table. The puck is moving to the right at 5 meters per second with respect to the 0 line marker. The table has markers painted on it, labeled from 1 through 5, and they are 1 meter apart. But this is no ordinary table. This table is capable of stretching as if it were a rubber balloon and can increase in length. We will use the line label 0 as our reference point. The painted labels will move to the right at a velocity proportional to their distance. The 1 marker at 1 meter of distance will move at 1 meter per second. The 2 marker at 2 meters distance will move at 2 meters per second, and so on. We can use this formula to determine the position of the puck and the markers as a function of time. By setting the puck and marker formulas equal to each other, we can determine the time it will take for the puck to reach each marker. As we start the animation, we see that the puck reaches the 1 marker quickly, but then it takes longer and longer to reach the rest. The puck can never reach the 5 marker, as it is moving at the same speed. The important thing to notice here is that the puck is slowing down relative to the surface of the table. In this chart, we plot the velocity of the puck with respect to the surface of the table as a function of time, and we see an asymptotic velocity decline curve. The puck is still moving at 5 meters per second with respect to the 0 marker, and it has not experienced any acceleration, but the velocity with respect to the table surface is continuously declining. This is the same effect that galaxies experience with the expansion of space. The expansion of space is given by Hubble's constant. For photons, the expansion of space results in a change of wavelength. If the air hockey table were expanding with an acceleration component, then the puck would decelerate much more quickly. That is what we see in this chart of the two falling objects. As the expansion of space increases the closer we get to the planet, the faster objects decelerate. The consequence of the loss of velocity in expanding space is a loss of momentum, resulting in lower time dilation effects. The loss of momentum effect has to also be present at the atomic and molecular levels. However, because the compression of space is greater for space falling to Earth, we can expect objects to experience a gain of molecular kinetic energy, expressed as a gain in temperature. This warming effect must also be present in our planet and on all celestial bodies. We can call it gravitational heating. We can also safely state that it has been constant for billions of years, and it is not a source of recent planetary warming. Since most matter is concentrated in areas of compressing space and less so in areas of expanding space, the implication is that new energy is being created in the universe, and by extension, new mass, given the equivalence between energy and mass provided by relativity. We now turn our attention to what happens when an object crosses from one space bubble into another. Let's say, for instance, an asteroid enters Earth's bubble. What we observe is that there are no changes in the relative velocity between the asteroid and Earth, other than gravitational effects. As the asteroid enters Earth's bubble, there is a change in momentum that can be calculated with the following figure. The initial momentum in the space bubble it comes from, minus the velocity of the space in the bubble it moves into at the point of crossing, minus the velocity of Earth's space bubble, multiplied by the rest mass. The edge of the space bubble is also where Doppler effects take place due to the change in momentum of photons. For non-relativistic velocities, the effects of the momentum change are not very noticeable, but they are more significant for relativistic velocities. Notice that the change of momentum for an object crossing a bubble boundary does not affect the overall momentum of the solar system. Conservation of momentum still holds.